Imagine a weapon that crosses borders without troops, leaves no craters, and makes machines destroy themselves while operators watch fake, perfectly normal readings. No missiles, no jets, no explosions, just code. That weapon exists. It's called Stuxnet, and it quietly rewrote the rules of warfare. In this video, we're unpacking the story of the first known cyber weapon designed to cause real-world physical damage. This isn't science fiction. Around 2010, a piece of malware slipped into one of the most secure nuclear facilities on Earth and sabotaged Iran's uranium enrichment program, years before most governments were ready to defend against anything like it. How did code jump air gaps, hide from antivirus, and trick highly specialized industrial machines into destroying themselves? Who built it, and why did they risk unleashing it into the wild? Stay with me, because the answers reveal the future of conflict, and it's already here. To understand why Stuxnet changed everything, we need to zoom out. For decades, warfare meant tanks, planes, ships, and missiles. Cyber attacks existed, but they mostly stole data, defaced websites, or caused financial damage. Then Stuxnet appeared, and for the first time, the digital world reached out and physically broke something in a targeted military-level operation. In this episode, we'll trace Stuxnet from the geopolitical tensions that sparked it through its ingenious technical design to the long-term consequences it had for global security. We'll break down how it infiltrated Iran's Natanz nuclear facility, what it did to the centrifuges inside, and why experts still argue about whether it was worth the risk. If you enjoy deep dive breakdowns like this, consider subscribing and turning on the notification bell so you don't miss future episodes. And definitely watch through to the end. We'll pull out the key lessons that now shape how nations plan for cyber war. Let's start with the geopolitical backdrop. In the early 2000s, Iran's nuclear program was accelerating, and Western intelligence agencies feared it was edging closer to acquiring the capability to build a nuclear weapon. Diplomatic negotiations and sanctions were underway, but there was intense pressure, especially from the United States and Israel, to slow Iran's progress without triggering an all-out war. A conventional airstrike on nuclear sites like Natanz would have been risky and politically explosive. Instead, somewhere in the shadows, a different idea emerged. What if you could quietly sabotage the program from the inside by attacking the machines running it? That concept reportedly grew into a covert operation often referred to as Olympic Games. Instead of targeting people or buildings directly, the plan was to silently degrade Iran's enrichment capability, wasting time, money, and resources, while hopefully remaining deniable. Stuxnet became the weaponized code at the heart of that strategy, embodying a new approach to power projection. To grasp why Stuxnet was so groundbreaking, we need to look at what it targeted: industrial control systems, specifically the systems running uranium enrichment centrifuges at Natanz. These aren't normal computers. They're specialized setups using programmable logic controllers, or PLCs, which translate digital commands into precise physical actions. Spin this rotor at this speed, open that valve, adjust this pressure. For years, these systems were considered relatively safe because they often sat on isolated networks, disconnected from the internet, an air gap. The belief was simple: if it's not online, it can't be hacked. Stuxnet shattered that illusion. It didn't just crash computers, it subtly manipulated how machines behaved while lying to the human operators watching. That required deep knowledge of Siemens industrial controllers, the exact model of frequency converters, and the physics of centrifuges themselves. In other words, this wasn't the work of random hackers. It was custom-built for one purpose: damaging a specific nuclear facility. So, how did Stuxnet actually get into Natanz if the systems weren't connected to the internet? The leading theory is almost mundane: USB drives and human behavior. The malware was designed to spread aggressively through removable media and local networks, lying in wait until it recognized a very specific environment. Stuxnet used a collection of rare, previously unknown vulnerabilities, so-called zero-day exploits, affecting Windows systems. These allowed it to run automatically when a compromised USB stick was plugged in, or when infected files were viewed. From there, it quietly moved laterally across networks, escalating privileges, and copying itself without raising alarms. Most of the places it landed weren't its real target. But that was part of the camouflage. By looking like just another worm spreading globally, it hid its true mission: to eventually land on engineering workstations connected, even indirectly, to those Siemens PLCs at Natanz. Only when it recognized that exact setup did the more sophisticated payload begin to activate. Once Stuxnet found the right kind of Siemens Step 7 engineering software and PLC configuration, its behavior changed from generic worm to precision weapon. The malware injected itself into the control logic programming process, effectively becoming a man in the middle between operators and the physical centrifuges. It recorded normal operating patterns over time, capturing data about rotor speeds and system responses. Then, while the operators thought they were sending safe commands and seeing genuine readings, Stuxnet began to subtly alter the instructions going to the centrifuges. Here's the key. It didn't just smash everything at once. The code altered spin speeds in carefully timed phases, speeding centrifuges up beyond safe limits, then slowing them down, inducing vibration and stress that would eventually cause them to crack or fail prematurely. Meanwhile, the displays in the control room showed playback from earlier, normal operation, masking the sabotage. To the humans watching, everything looked fine, until equipment started breaking with no obvious cause. From a technical perspective, one of Stuxnet's most impressive feats was its use of multiple zero-day exploits, vulnerabilities unknown to software vendors and the public. At its discovery, it was using at least 4 separate Windows 0 days, an almost unheard-of concentration of valuable exploits in a single tool. This alone pointed to a nation-state level operation. 0 days are expensive and rare. Burning several at once on a single campaign suggests deep resources and urgent strategic priorities. Stuxnet also carried legitimate but stolen digital certificates. These certificates are like cryptographic ID badges that tell Windows, you can trust this software. By signing parts of its code with certificates taken from real companies, Stuxnet slipped past many security checks that would normally flag unknown or suspicious software. Combine that with extremely specific PLC payload logic, and you get something far beyond typical cybercrime. This was carefully engineered sabotage designed to blend into a target environment, evade detection, and accomplish its mission with surgical precision. Let's talk about the physical impact. Natanz used thousands of gas centrifuges arranged in cascades to enrich uranium. These machines are tall, rapidly spinning cylinders. They must run at very specific speeds and remain perfectly balanced. Even small irregularities over time can cause failures. Stuxnet's payload manipulated rotor speeds in subtle periodic bursts. Reports suggest it alternated between gradually ramping up the speed far beyond design limits, then suddenly slowing down or oscillating speeds in patterns that stressed components. This didn't always lead to spectacular explosions. It often produced unexplained equipment degradation and higher failure rates. Estimates vary, but many analysts believe Stuxnet destroyed roughly 1,000 centrifuges and set Iran's program back months or even years. Crucially, the operators at Natanz initially had no clear explanation. To them, it looked like design flaws, manufacturing issues, or bad luck, not a foreign power quietly reaching into their facility through code. Just as fascinating as the attack itself is how Stuxnet stayed hidden for so long. Its designers anticipated defensive tools and built multiple layers of stealth. First, it limited how often and how far it spread, using checks to avoid uncontrolled exponential growth that might draw attention, though it still eventually escaped into the wider world. On infected engineering stations, it carefully modified project files to insert its own logic while presenting them as untouched. Inside the PLCs, it intercepted sensor data, replaying previously recorded good values back to monitors. That meant even diagnostic tools could be misled. Stuxnet also employed rootkit techniques at both the Windows level and the PLC level, hiding its presence from file listings and system utilities. When certain conditions weren't met, wrong hardware, wrong software version, it stayed mostly dormant, reducing anomalous behavior that might spark investigation. This blend of operational security and technical stealth made it one of the hardest to spot pieces of malware of its time. The secret didn't last forever. In 2010, a small cybersecurity company in Belarus, VirusBlock Ada, noticed an unusual piece of malware causing unexplained system issues in Iran. They flagged it, and soon major security firms like Symantec and Kaspersky Labs began dissecting what became known as Stuxnet. What they found stunned the industry, an extraordinarily complex worm targeting Siemens industrial systems using multiple 0 days. Researchers gradually pieced together its architecture, separating the propagation mechanisms from the highly specialized PLC sabotage routines. As analysis reports circulated, it became clear this wasn't cybercrime. There was no attempt at financial gain, data theft, or mass destruction. The code's focus on a narrow hardware configuration, combined with geopolitical context, led many to suspect a state-sponsored operation aimed at Iran's nuclear program. Public disclosure of Stuxnet triggered a wave of alarm. If this level of cyber-physical sabotage was already in the wild, what else might exist quietly waiting inside power plants, pipelines, or factories? Officially, no country has fully admitted to creating Stuxnet, but extensive investigative reporting, leaked documents, and unnamed sources strongly suggest it was a joint project between the United States and Israel. The codename Olympic Games has appeared in several accounts describing a broader campaign to slow Iran's nuclear program. According to these reports, Stuxnet wasn't a one-off. Earlier versions were allegedly tested on replica centrifuges built in US facilities, refining the attack until it could damage Iranian systems without causing catastrophic, obviously hostile failures. From a strategic standpoint, Stuxnet offered plausible deniability. Physical damage could be framed as technical malfunction rather than open aggression, but this ambiguity cuts both ways. Once Iran and the rest of the world realized they'd been targeted by a cyber weapon, it set a precedent. If major powers were willing to cross this line, others might follow. The result was a quiet but profound escalation in global cyber arms development. Stuxnet's revelation sent shockwaves through industries that relied on industrial control systems, power grids, water treatment facilities, oil and gas pipelines, manufacturing plants, even transportation networks. Many of them used similar architectures. Windows workstations talking to PLCs over field buses and proprietary protocols, often with minimal security. Suddenly, it wasn't theoretical. A sophisticated adversary had shown that you could cross air gaps, understand niche industrial processes, and cause physical damage with code alone. Governments and companies scrambled to reassess their defenses. Security researchers began finding other malware families, apparently inspired by Stuxnet, like Duke and Flame, focused more on espionage and reconnaissance. Frameworks emerged for securing industrial control systems, but retrofitting security onto decades-old equipment proved difficult and expensive. Perhaps the most unsettling realization: many critical systems had been designed assuming obscurity was enough protection. Stuxnet demonstrated that determined attackers were willing to invest the time and money needed to pierce that obscurity completely. Ethically and legally, Stuxnet opened a Pandora's box. Was it an act of war, sabotage, covert action? Under international law, there's still debate over how to classify cyber operations that cause physical damage without casualties. Supporters argue that, compared to bombing Natanz, Stuxnet minimized loss of life and reduced the risk of a broader regional conflict. Critics counter that it normalized attacking civilian infrastructure and invited retaliation in kind. If nuclear facilities are fair game, what about hospitals, power grids during winter, or water systems? Another concern is proliferation. The moment Stuxnet escaped into the wild and was analyzed, its techniques became a blueprint for others. Even if the exact payload was narrowly tailored, the overall playbook, infect, hide, manipulate industrial processes, could be adapted. We're now in a world where mid-tier states and eventually sophisticated criminal groups might pursue similar capabilities. The norms we build, or fail to build, around cyber warfare today will shape how bad future conflicts become. Let's pull together the key lessons from Stuxnet. First, it proved that cyber weapons can have kinetic, real-world effects, breaking machines, not just stealing data. That moved cyber operations from the margins of conflict into the core of modern military strategy. Second, it exposed the fragility of critical infrastructure. Systems once assumed to be safe because they were isolated or obscure turned out to be vulnerable to determined, well-resourced attackers willing to study their quirks in detail. Third, Stuxnet highlighted the blurred lines between war, espionage, and sabotage. It damaged a nuclear facility without officially declaring war, setting precedents that still worry diplomats and ethicists. Finally, it sparked a global race. On one side, nations developing more advanced offensive cyber tools. On the other, defenders rethinking how to protect industrial systems, supply chains, and even everyday devices. Understanding Stuxnet isn't just historical curiosity, it's essential context for the threats shaping our future. So, where does all this leave us? Stuxnet marked the moment the world realized that the battlefield now includes server rooms, engineering workstations, and factory floors. The same connectivity driving efficiency and innovation also opens doors to sabotage on a national scale. For you and me, this isn't just a distant geopolitical story. It affects how secure our power, water, transportation, and even hospitals are in a crisis. It's why cybersecurity isn't only about passwords and antivirus. It's about the resilience of the physical world we depend on. If this deep dive into Stuxnet helped you see cyber warfare in a new light, consider subscribing and hitting the notification bell so you don't miss future investigations into the technology shaping modern conflict. Drop your thoughts or questions in the comments. Do you think Stuxnet was justified or a dangerous precedent? And if you know someone interested in cybersecurity or geopolitics, share this video with them. Stay curious, stay critical, and stay safe online.